Chapter 8: Waves. Now, when a stone is dropped in a pool of still water, ripples are created on the water surface. These ripples form concentric circular rings around the source of disturbance and spread outward along the surface. These ripples are called waves. When these waves reach a point on the surface of water, the point starts oscillating up and down. However, an object floating on the water at this point is not tossed or moved away. We say waves do not transfer matter, only energy. By definition, a wave is a disturbance that travels or propagates through medium or space. And that definition divides waves into two broad categories. Those that propagate through media are called mechanical waves, while those that propagate through space are called electromagnetic waves. In this chapter, we shall talk about mechanical waves. We shall deal with electromagnetic waves in Form 4. Mechanical waves require material medium for propagation, either solid, liquid, or gaseous media like air. They cannot propagate through vacuum. Water waves, sound waves, and seismic waves are mechanical waves. Mechanical waves occur when a disturbance causes vibration of particles of the medium of propagation. For example, when a slinky spring fixed on one end and a disturbance created on the free end, we observe a disturbance carried to the fixed end of the slinky. Mechanical waves can further be classified into transverse and longitudinal waves. This depends on the relationship between the direction of displacement of the particles in the medium and the direction of propagation of the wave. In a transverse wave, the medium particles vibrate in a direction perpendicular to the direction of the wave travel. While in a longitudinal wave, the particles of the medium vibrate in a direction parallel to the direction of the wave travel. In both waves, it is only the disturbance that propagates and not the particles. The particles only vibrate about their fixed positions and transfer the energy to their neighboring particles. We start with transverse waves. Now, we tie one end of a string 5 meters in length to a pole and hold the free end tightly so that the string is taut. We jerk the string by moving the hand up and bringing it back to its initial position. A pulse is created and travels along the string to the fixed end and dies down. This pulse moves with a certain velocity, v. When the hand is moved up and down continuously about the mean position with a simple harmonic motion, a continuous wave, which is sinusoidal in shape, travels along the string with a velocity v. If you mark a point anywhere on the string, you will see that the point moves up and down and never towards the fixed end. This sinusoidal wave is a transverse wave. Water waves are a good example of transverse waves. Another example is a slinky spring jerked up and down. Next, longitudinal waves. Now, consider air with lots of dust particles trapped inside a glass tube with a piston. The tube is placed in a dark room with a focus light behind the tube. When the piston is pushed into the tube with a jerk, we see the dust particles near the piston are compressed and form a band. This is due to an increase in air pressure created by the piston on the particles. This compression band moves to the other end of the tube as a pulse and dies down. When the piston is pulled back, the pressure at the compressed region decreases and causes the dust particles to move back to their original position. The low pressure region is called rarefaction. When the piston is moved back and forth, we see a series of compression and rarefaction bands formed by the dust particles inside the tube moving towards the other end. These bands constitute a longitudinal wave. Sound waves are longitudinal waves propagated through air. When sound is produced, it compresses or expands a small region of air near the source. This causes a change in the pressure of air in that region. The increased pressure causes compression of air particles surrounding the source. These particles in turn transmit pressure to the neighboring particles, which get compressed. After transmitting the pressure, the particles near the source return to their original position and expansion takes place. This cycle continues as particles compress and expand as they transmit pressure to their neighboring particles, forming bands of compression and rarefaction that travel from the source through air. A fixed slinky spring with one end free also generates longitudinal waves when a disturbance is introduced on the free end. So, when a single vibration is sent through a medium, a pulse is generated. The pulse can be transverse or longitudinal. When the vibration is continuous, a series of waves move continually away from the source and are said to be progressive. Again, they can be transverse or longitudinal. Next, characteristics of wave motion. Wave motion is described as repeated, periodic or oscillatory, just like the motion of a pendulum or the vibration of a spring. Suppose we have a spring attached to a stationary surface, and on the other end of the spring, there is a block of a particular mass. If we pull this block so as to stretch the spring, and then release it, it will vibrate back and forth between the compressed and stretched states. If we assume this surface is completely frictionless and we graph the position of the block against time, it will display a sinusoidal behavior. We saw in sinusoidal wave that particles vibrate up and down about their mean position. The maximum displacement on either side of the mean position is called amplitude A, measured in meters. The highest point on the positive side is called a crest, and the lowest is called the trough. Wavelength lambda is the distance in the x direction between any two consecutive repetitions of the shape of the wave. It is the distance between any two consecutive crests, troughs, or any two consecutive points in the same phase of the wave. Period T is the time taken by a wave to complete one cycle or oscillation. It is measured in seconds. Frequency is the number of cycles made in 1 second. It is given in hertz. Speed V is the distance covered by a wave in 1 second. It is different from frequency. Frequency is determined by the vibration source, while speed is determined by the medium of propagation. Mathematically, frequency is equal to 1 over period, and so period is equal to 1 over frequency. We also know that speed is given by distance over time, and therefore speed is equal to wavelength over period. But period is equal to 1 over frequency, and so speed is equal to wavelength divided by 1 over frequency, and that gives us speed is equal to frequency times wavelength. Let's take an example. Determine the speed and wavelength of a wave of frequency 3 Hz if it takes 4 seconds to cover a distance of 12 meters. So speed is equal to distance over time. 12 meters over 4 seconds gives us 3 meters per second. And speed is equal to frequency times wavelength, meaning that wavelength is equal to speed over frequency. This is equal to 3 meters over 3 Hz, giving us 1 meter. And finally, phase and phase difference. Now, two waves can have the same amplitude but different frequencies. They could also have the same frequency but different amplitudes. Usually, the wave with the higher frequency has a smaller period. And that simply means if the vibrations are faster, it takes a shorter time to complete one cycle. Consider two similar pendulum bulbs A and B on your screen. If both are displaced towards points P and released simultaneously, they will be set in oscillation. Both will pass through point O at the same time and moving in the same direction. They will reach the highest amplitude Q at the same time and swing back to P to complete one full cycle. At any given time, the two will be at the same level of displacement and moving in the same direction. They are said to be oscillating in phase, and their sine waves are exactly the same. If the waves are given initial displacements of equal magnitude, but in opposite directions, both will pass through point O at the same time, but moving in opposite directions. They also reach positions of maximum displacement at the same time, but in the opposite directions. Such oscillations are said to be out of phase. In this case, they are 180 degrees out of phase. This is the phase difference. And what if both are initially displaced at the same level on the same side, but released at different time intervals? They reach different positions at different times. These two are out of phase.